Extreme Physics.
All right, this is 2016 APC Mechanics exam. A cart of mass M is pulled along a level dynamics track as shown above. A force sensor is attached to the cart with a string and used to measure the horizontal force exerted on the cart to the right. A motion sensor is used to measure the acceleration of the cart with the positive direction towards the right. Friction is not negligible. On the dot below, which represents the cart, draw and label all the forces, not the components that act on the cart. Each force must be represented by a distinct arrow starting on and pointing away from the dot. All right, we got our cart. Boom. And we got something pulling it. Circle the object of interest. Let's draw ourselves a free body diagram. We would just do it on their dot. But anyways, we got the tension force this way. They said there's friction. So friction's that way. It's going to be smaller than tension force, I would imagine. Normal and weight. All right, so that's what that should look like. It's pretty straightforward. A student pulls the force sensor with a constant force and the car accelerates. This is repeated for several trials with different constant forces for each trial. The data below in the table. All right. So you got to plot acceleration versus force. All right. I'm not going to do that. I could do it on the board. The College Board printed out theirs. So I think we're pretty good at plotting data points. Make sure you're using the whole graph. And be careful on your line of best fit. All right. Using the straight line from the graph, calculate the mass of the cart. Let me talk about this graph. I'm not going to actually graph it. I'll just kind of sketch it. So you can get something like this. So we got our force and we have acceleration, and then we got some data. So you should have had some data like this. If this was zero force, if this was 0, 0, right? If you plotted it like that, you should have got something like that, and then you would have drawn your line of best fit, something like that, and you would have had a force intercept, and the graph would have intercepted the f-axis. So it says, using a straight line from the graph, calculate the mass of the cart. Well, what we're going to have here is we're going to have, applying Newton's second law to that, we got sum of the forces equal mass times acceleration. And so we're just going to look at the x forces, though, equal mass times acceleration. And the forces are going to be, we had, to the right we had tension, and to the left there's going to be friction equals mass times acceleration. So what this line is, really, is, let's get A by itself. A equals T minus F over M, right? So that's the mathematical relationship. And we want to look at this like, just y equals mx plus b, like that. So what we'd end up with our graph, this F equaled the tension force, right? That was the tension force. This force was the force sensor reading. That was the tension force. So let's get that in, so it's looking more like that. So it's looking more like this. So we would have here then y equals x is t. So you'd have t over m minus f over m, right? All right. So this is our x variable. That's x. That's the force or the tension. 1 over m is the slope. Slope equals 1 over m. In fact, I could rewrite that. Let me rewrite that so it's more obvious. Let's really deconstruct this thing. Let's really deconstruct this thing. Let me write it like this. Let me say it's equals 1 over m times t. So t is the horizontal variable, usually x. The slope is 1 over the mass. Those are different m's, of course. This represents slope. This m represents mass. Minus, and then the y-intercept occurs down here, which makes sense. Yes, it's in a negative position, right? So, all right. Now, this right here is the slope, right? So how are we going to find the mass? We're going to calculate the slope. Slope equals 1 over mass. Mass equals 1 over slope, right? So that's what we would do. So it says, using the straight line from the graph, calculate the mass of the cart. So you would find the slope, right? And I know you can find the slope of a straight line. I'm just going to use the value that the College Board got. So when they did that, when they plotted their line of best fit, they chose 2 points. Make sure you're doing that. Maybe, chose 2 points anywhere along this line, convenient points. I usually go for when we got 2 lines crossing on our grid is a convenient way. So you're going to do that, and you're going to go change an A over change an F. So the College Board in their calculations got the slope equal to 2.16 kilograms to the minus 1. All right. And therefore, the slope, or m, equals 1 over 2.16 kilograms. Which I guess is 0.463 according to what they did, right? So just plot your points, draw a line of best fit, calculate the slope. The heavy lifting was here, understanding that setting up a model that represents this, which is we want y equals mx plus b, or a equals slope f plus y-intercept. I'll just call it b. Right? Now, the way we drew this, we can't really see where the y-intercept is. But anyways, all right, so there you go. We got, that's not too bad. It's going to take you some time to graph. Be careful with your graphs. You don't want to lose points because your points are in the wrong position. Using the straight line from the graph, determine the magnitude of the force of friction. All right. Well, the way I would do it, I'd take a look at this relationship here, and I got acceleration equals t over m minus f over m, right? So when a is 0, right, because this is the point at which a is 0, right, the acceleration is 0, equals t over m minus f over m. All right, so now we could, and then we could solve this for f, right? So we got f over m equals t over m, right? M's go away, so f equals t at a equals 0, right? So F equals T. The friction equals the tension when the acceleration is 0, right? You keep pulling and pulling and pulling. Friction keeps pulling back. Nothing's moving. And then all of a sudden you start accelerating. That's the point at which you have exceeded the maximum friction force, right? So, so F equals that. And then so I would just look at my graph. and where is that intercept. Now, the way the College Board did it, in their graph, they didn't actually show the horizontal intercept, right? I actually included it in mine, and I used plenty of the graph, and I just did that. And anyway, so use your x-intercept to do that. I thought that was the easiest way. And 0.272 newtons, right? So that point here is 0.272 newtons, right? That's the point at which it just starts accelerating because the force you're pulling with is exceeding the maximum friction it can pull back with, right? And then that friction should stay constant because it's kinetic once you're going. The above experiment is repeated by using a constant force sensor reading of 0.45 newtons. The cart starts from rest at time t equals 0 and is pulled for a time 2 seconds along the dynamics track. Determine the acceleration of the cart. Okay, acceleration equals F net, which is, of course, the tension minus the friction divided by the mass. Determine the acceleration of the cart. So they said we're going to use a constant 0.45 newtons. That's going to be our tension. Minus friction. What did we say friction was? So 0.272 newtons divided by 0.463 kilograms. 0.384 meters per second squared. I'll give us an extra one. Go with an extra digit there. The string breaks at 2 seconds. Calculate the time it takes for the cart to stop after it breaks. All right. Well, after it breaks, acceleration equals minus F over m is negative 0.272 newtons divided by 0.463 kilograms. 0.5875 meters per second squared. That's a negative. Right, so that's the acceleration after the break. This is after the spring breaks. After spring breaks. After string breaks. String breaks. All right, so that's the acceleration after it breaks. This is the acceleration before. So we're going to have to figure out how fast was it going, and then how long is it going to take to stop, right? So I'm going to draw myself a picture because I'm getting confused, right? So, and we got T, and at 0, V equals 0. V0 equals 0. And then at time 1, the spring breaks. The string breaks there. Here's the string, and it breaks. I don't know why it broke. So that's V1, and then finally it stops at position 2, and V2 equals 0. Right? It's not moving anymore. All right. So to figure out, and we want to know, but here between the acceleration from 0 to 1 was 0.3844 meters per second squared. And the acceleration from 1 to 2 is negative 0.5875 meters per second squared. All right, so we had an acceleration this way. So I think what we're going to do is figure out what V1 is. Let's find V1. Let's calculate V1. Starts from rest and accelerates for 2 seconds. T0 equals 0. T2 equals 2 seconds. And we want to know what T3 is, right? But really, we want to know the difference in T2 and T3 because they want to know, calculate the time it takes for the cart to stop after the spring breaks. So We'll calculate T3, but then we'll subtract from it T2 to get that time. I'm going to erase this. Erase that. And this is the acceleration from 0 to 1. And this is the acceleration from 1 to 2. I'm going to need this room here, I think. V1 equals V0 plus AT from 0 to 1. So this is 0. So V1 equals 0.3844 meters per second squared times 2 seconds. 0.7689 meters per second. All right. And we know that V2 equals V1 plus acceleration from 1 to 2 times delta t from 1 to 2. And that's 2 seconds. So we want to know what that is. Oh, no, that's not 2 seconds. We want to know what that is. Delta t from 1 to 2 equals question mark, right? Let's just solve for that. V2 is 0. All right. So this is minus V1 over A. 1 to 2. And V1 is 0.7689 meters per second divided by, that's negative, because that's negative. And the acceleration is negative 0.5875 meters per second squared. All right, so I got like 1.31 seconds. The experiment and analysis in parts A and B are repeated with a cart that has the same mass, but a greater force of friction. Will the slope be greater than, less than, or equal to? Too bad I erased everything. I need a bigger board. I gotta recreate some stuff. Let's get rid of all this stuff. We had acceleration equals the force minus friction divided by the mass. So we had 1 over m is the slope. F was the x-axis minus f over m. Right? So we had that relationship right there. All right, now this is going to be bigger. We're going to make that bigger. All right, well, we're going to get less acceleration, but will the slope of your new line be greater than, less than, or equal? Is the slope. Did the mass change? Nope, I don't think so. So therefore, slope same, and slope is the same. Will the horizontal intercept for your new line be less than or equal to the intercept b? It would be, since friction is greater, the intercept would be greater, right? Because we have this, we just have this graph here, and we have acceleration, and we have force, and we have a line like that. There's our horizontal intercept. And when does that occur? That occurs when A is 0. So we got A equals, so we take our equation, set A equal to 0, and I already did this earlier, but we'll do it again, right? This is the friction. Where this intercept is F. That's the friction, right? And if friction is greater, that intercept will be greater. The line would be like, that's greater F. Well, the slope should have been the same. That's not quite the same. But anyways, I didn't draw those very parallel. They should be. Imagine they're parallel. All right, M's go away, and F equals F, right? When A is 0, this intercept is F, and if F is bigger, then I'm gonna redraw that so it looks parallel. Let me stand right here. Right? So that's new, greater F, greater friction right there, right? So that got bigger. All right, that's the end of that one. All right, so that was the end of question 1. Question 2 of 2016. We got a weird looking spring. A block of mass 2m rests on a horizontal frictionless table. All right, frictionless. I like frictionless. and is attached to a relaxed spring. Spring's mellow. As shown in the figure above, the spring has a nonlinear. It's nonlinear. It's not an ideal spring. So F equals minus bx cubed. Of course, that negative just means that if I displace it in the positive direction, I'm going to get a negative force. If I displace it in the negative direction, I'm going to get a positive force. That just means the force is in the opposite direction of displacement. That's all that negative means. Nothing more than that. So be careful with that. Don't just blindly plug negatives in. All right. Where B is a positive constant and X is the displacement from equilibrium for the spring. A block of mass 3m and initial velocity v0 is moving to the left as shown. All right. On the dots below, which represent blocks of mass 2m and 3m, draw and label the forces, not the components, that act on each block before they collide. Each force must be represented by a distinct arrow starting on and pointing away from their appropriate dot. All right, well, we got M here, and it's got a the spring attached to it, but it's equilibrium position. That means this thing's not applying a force either way. So the only thing applying a force to this thing is we got the up we have the normal force, and down we have the weight. 2 mg down, and they should be equal to each other. And then we have this other one. Same thing. It's just going sliding along frictionless, and we got normal. I'll call that normal 3, normal 2, and we got 3 mg. All right, there you go. Beauty. Those are some easy points. Bet you get 4 points for that. That's pretty good. Don't mess that up. The two blocks collide and stick to each other. The two-block system then compresses the spring a maximum distance d as shown above. All right. Express your answer to parts B, C, and D in terms of M, B, V0, and physical constants as appropriate. Always be appropriate. Derive an expression for the speed of the blocks immediately after the collision. All right. Got to erase because I have myself a small whiteboard. So the blocks are coming in and they're going to hit, and mechanical energy will not be conserved. They're going to hit and stick together. Mechanical energy is not conserved in this case, but momentum is. This is an isolated system. There's no friction on the track. So let's go before and after. We got 3m, and it's going like that. We got V0, and then we got right before, we got that, and then right after. Now there's a spring there, but it's not applying a force yet. And right after the collision, it won't have compressed enough to having applied any significant force, right? The spring is there, but it's not compressed yet. This is right after. So momentum of 0 equals a momentum of 1, because this is an isolated system. It's closed too. Closed is easy. Doesn't gain or lose mass, and there are no external forces. Now there will be later, right? If you waited 1 second later, you couldn't use conservation of momentum because it's not isolated, because the spring would be pushing back. It's not pushing back yet, though. All right. So the only thing that has momentum initially is this thing, and it's its mass, which is 3m, times its velocity. That way. Everything's in the same direction, so we don't have to be too careful with our directions in this particular problem. Afterwards, we have two things moving at a speed I will call v1, and it's 3m plus 2m, which is 5m times v1, right? Because they're moving together. And okay, we can get rid of the m's. So what do we got? We end up with 3/5 v0 equals v1. All right. Derive an expression for the kinetic energy of the two-block system immediately after the collision. All right, I think I'll do that right away. That's kind of easy. So kinetic energy at time 1 equals 1/2 mass, which is 5m v1 squared, which is v1. This is v1 right here, so it's 3/5 v0 squared, right? 1/2 mv squared. All right, so what do we got here? We have 5/2 m 9/25 v0 squared. Let's see. So I could make this a 5 and make that a 1. And then I would end up with 9/10 m v0 squared. That's the kinetic energy. Derive an expression for the maximum distance. All right, so I think we're going to need to erase. Now, we can't use this relationship here. Oops. Especially since it's gravity. The potential energy of spring is 1/2 k x squared. We can't use that because that's only for an ideal spring, right? So that's not true in this case. Because in an ideal spring, F equals negative kx, right? And that's not what we have here. So, I think we're going to have to do some calculus. We had our spring, and it's compressed. And this is 3m and 2m. So we got this block of 5m, and everything went from to some distance d, right? And it compressed. At its maximum compression, all this kinetic energy went to spring potential energy, right? So it's really the work that the spring did. So all this energy, kinetic energy, is going to end up as spring potential energy. This is going to stop. There's no friction, and the force that a spring applies, this is going to be a conservative force. The spring is nonlinear, but it doesn't mean it's lossy. We assume that there's no losses, that this is a conservative force. Springs have conservative forces. Let's figure out how much work was done. All right, so we could use the network equals change in kinetic energy theorem, right? So this is going to be the change in kinetic energy, and this is the network that the spring is going to do on the block. So now we're just looking at the block as a system, and we're going to look at the network done on the system. Weight doesn't do any work, and neither does a normal force. The only thing it's going to do work is the spring, and it's going to apply a force this way while it displaces that way, and that's going to change the kinetic energy. All right. To figure out the network, we're going to take the integral of F spring dx equals delta x, right? And the spring's applying a force that way. And this is going to go from 0 to d. And what are we calculating? D? Yeah, we're calculating d. All right, so we're going to go, I'm going to start over here because I may need room. So we got bx cubed dx as x goes from 0 to d equals delta k. Which in this case is going to be, right, delta k. I'll call this 2, position 2 when it gets here, and position 1. So delta k is k2 minus k1, right? So we're going to end up with a negative b x to the 4th over 4 d to 0 equals k2 is 0 minus 9/10 mv0 squared, right? So b d to the 4th over 4 equals 9/10 mv0 squared. D to the 4th equals, yeah, right, equals 3.6 m over b v0 squared. So d equals 3.6 mv0 squared over b to the 1/4 power. In which direction is the net force, if any, on the block of 2m when the spring is at maximum compression? Well, the whole system, if we take a look at the whole system, there's a net force this way, right? It's compressed. So there's a net force to the left. So the whole system, these two are accelerating to the left because there's a net force to the left. And if this is accelerating to the left, then there's a net force on this. Even though 3m's pushing on it, the spring must be pushing more. So the answer is to the left. There is a net force to the left on 2m. Because if we look at this as one block, clearly if this is compressed, there is a net force this way, right? So, yay! Is to the right, I guess. There's a net force to the right. Did I say left? I don't know what I said. It's to the right. It's that way. That way's right. Right? So it's to the right. Which of the following correctly describes the magnitude of the net force on each of the two blocks when the spring is at maximum compression? The magnitude of the net force is greater on 2m. It's greater on 3m. The magnitude of the net force has the same non-zero value on both, or the magnitude of the net force on each block is 0. Justify your answer. All right. Well, these two are moving together, right? It's pushing that way. They're together. They're going to move together. They're going to have the same acceleration. The acceleration of this one is going to be the same as the acceleration of this one. If the accelerations are the same, that means that this must have a greater force on it because it has more mass, right? So acceleration equals F over 3m. I'll say F3. And acceleration equals F2 over 2m. Right? So in order for these to be the same accelerations, this must have a greater force on it because it has greater mass. Right? So what was the answer? The magnitude of the net force is greater on 3m because they're accelerating at the same rate. It has more mass, so it must have more net force on it. So there you go. I justified my answer. Do the two blocks which remain stuck together and attached to the spring exhibit simple harmonic motion after the collision? All right, those of you taking the exam in 2020, you don't need to answer this question because we haven't done simple harmonic motion. Simple harmonic motion isn't going to be on the test and the exam. But everybody after that, no, this will not exhibit simple harmonic motion because this is not a linear restoring force. The only time you will see simple harmonic motion is when there's a linear restoring force on it, like an ideal spring, F equals negative K delta X. If there is a linear restoring force on an object, if that's the net force, it will be in simple harmonic motion. That is not. And that's the only condition you're going to be in simple harmonic motion. So, no, it's not. And that concludes question 2. Let's go to question 3. Question number 3 from the 2016 exam. Oh, we got this weird looking thing. A uniform rod of length D, all right, has one end fixed to a central axis of a horizontal frictionless circular platform. All right, so this thing's spinning like this. It's horizontal. Oop, I shouldn't hold it down there. I should hold it up here. It's spinning like this. It's you know what? I think I can grab my wheel. So we got a horizontal platform. It's rotating like this. It's horizontal. Always make sure when you got these things, is it vertical or is it horizontal? In this case, it's horizontal. I guess I'll draw this. Give you a quick sketch. I'm going to overlay a printout on the video, but let's. This one's going to be weird because they have all these weird lengths. You have to pay close attention to what length is what, and it's kind of odd. All right, so R is 2D. That's D. That's D over 2. This is eventually going to stretch out to another D, so that's actually going to be at the end. Fixed at the other end is an ideal spring of negligible mass, all right, to which a block is attached. The block is set in frictionless grooves. All right, cool. I like frictionless. So they can only move along a radius of the platform as shown in figure 1. So this thing can only move like that. The equilibrium length of the spring is d/2, right there. Below is a table showing the mass of the block and masses and rotational inertias of the rod and platform. All right. A motor begins to slowly rotate the platform counterclockwise as viewed from above until the platform reaches a constant angular speed omega. Under these conditions, the spring has stretched an additional length d/2 as shown in figure 2. Actually, I shouldn't have had that omega there. That was later. That's when it stretched out there. So this thing's eventually going to make it to here. One thing they didn't mention, which they should have, is that block is small. So essentially having no size. They kind of didn't mention anything like that. We have to assume that in this problem because they didn't give us any other information. Answer the following questions for the platform rotating at constant angular speed omega. Express all algebraic answers in terms of md, omega, and physical constants as appropriate. Derive an expression for the spring constant of the spring. All right. Well, spring constant is we basically have two ways of finding it. We can either use that, which is Hooke's law, or 1/2 k delta x squared. Right. But we got this thing in circular motion. Once it gets out here, it will be going omega, so we know its speed. So I think we're going to use Hooke's law, and we're going to use Newton's laws because this thing's in circular motion. That block is in circular motion, and I circle the object of interest. I got something like this. As it spins around, there is a force towards the center, right? There's a spring attached to it, and I circle it, and I'm going to draw a coordinate system. I'm going to use my RTZ coordinate system. The center of the circle is this way, so I'm going to make that my R-axis, and we got our tangential axis, but that's probably not going to come into play here. So we have this force, which is the force of the spring, is pulling in like that, right? Now we also had the normal force and the weight into the plane, but that's not going to enter into this. So the sum of the forces in the R equals mv squared over r. This is in circular motion. This is a radial acceleration due to a radial force, or m omega squared r. We're going to use that one because that's what we know omega. And no v. So anyway, so let's do that. So we have the spring force. So the spring force equals m omega squared r, but the spring force is k delta x r. I'm not going to worry about the negative because I know what the negative means. It's just talking about direction. I've already taken into account direction. Don't just slap a negative on there. Know what the negative means. Right? So just going to drop that in there like that. And, we know delta x. Delta x is d/2, I guess. So k d/2 equals m omega squared. And what's r? R is 2d in this case. When it's all the way out there, it's all the way out there, and that's at position 2d. D can go away. All right, so we want the spring constant. So k equals 4m omega squared. All right. That is our spring constant. Not to be confused with kinetic energy. Lowercase k. Determine the expression for the rotational inertia of the block around the axis of the platform. All right. So we want the rotational inertia of the block. Rotational inertia is going to equal m. What is the mass of the block? It's m. M times r squared, which is 2d is r squared. is m times 4d squared. So you have to be careful with our lengths. Like I said, it's kind of weird in this one. So this is I of the block. About the center is calculated about the center. That is BI. Derive an expression for the rotational inertia of the entire system. All right, so we just gotta add these up. Just gotta add them up. Remember, moment of inertia is a scalar, right? We just add them up. It's just the addition of every hunk of mass as it goes around, and it's distance squared from the point of rotation. That's all it is. We're just adding them up. So it's a scalar operation. All we gotta do is add these things up. I total equals I block plus I rod plus I platform. I plat. All right. I block. That's what we just did. That was 4md squared. Plus I rod is mass of the rod, which is 3m. See the squirrely stuff they're doing? It's 3m. Mass of the rod times d squared over 3. All right. Plus mass of the platform, which is 5m, times r squared, which is 2d, divided by 2. I'm just getting this from that table. All right. We just have to be careful with what we put in for mass and r and stuff like that. That's all. That's all. All right. So what do we got? We got 4md squared plus md squared. We got 3 over 3 plus, let's see, 20 md squared, right? Right? I did that right. 2 times 2 is 4. 4 times 2 is 4. Or 4 times 5 is 20 divided by 2. So that's going to be 10. What do we end up with? 15? 15 md squared. Is that I? What am I stepping on? Oh, I don't want to step on wires. 15 md squared. All right. Determine the expression for the angular momentum of the entire system about the axis of the platform. All right, so we got something spinning. You know, anytime we got something spinning, we know that, angular momentum in general is r cross p, right? If we're taking a look at just particles and stuff like that, it's r cross p. But if we have something that's spinning around an axis like this, we're not going to use r cross p. We're going to use I omega, right? Anything, spinning on an axis or something thrown up in the air and rotating freely and stuff like that, we're going to use I omega, these rotating things. We're not going to use, we're going to use this when we got a situation like they go, hey, now we got a wheel, and we're shooting a dart at the wheel, and there's a mouse on the wheel, and we want to know the mouse and the wheel, how fast they're going to be going. In this case, we are going to find, we got the wheel, and the dart's going to hit it, and angular momentum is going to be conserved because there's no net torque on the system. But to calculate the angular momentum of this, we're going to have to use r cross p, right? And we would set up our coordinate system, and this thing would come in like that, and it would have velocity. We could figure out the momentum, and then this would be that would be the, r is like this, but this is the moment arm here, so we would use that r, and we would just multiply that by p. But that's not the case in this situation, but that might come up. That's another way to do it. That's another way in a different situation to find angular momentum. In this case, we're going to find angular momentum because we just have something spinning on an axis. We're just going to say that's I omega, right? All right. And we conveniently just found I, which was 15 md squared. And omega is omega. Well, that was kind of easy. All right. C. Angular momentum is 15 md squared. Omega. Okay, now that was pretty easy, and you should start thinking, well, maybe they're leading me down a path to solve something else. Maybe they're giving me a hint. Or maybe they're being dastardly and leading me down the wrong path. We'll see what the College Board is up to here. While the system continues to rotate, a small mechanism in the pivot moves the rod slowly until the center of the rod is positioned in the axis. All right, so that's kind of a weird thing. Let's see if I can recreate this. I'm probably going to fail miserably. So as this is rotating, I need a rod. This is the closest thing I have to a rod. All right, so I'll use this part of it. We're just gonna look at this part. We're gonna ignore that this even exists. So this is going around. This is going around a circle like that, right? And what's gonna happen is this rod is gonna start moving in like that, and it's gonna start pulling the whole spring mass thing in like this. It's going as it's rotating, right? It's going. While the system continues to rotate, a small mechanism in the pivot moves the rod slowly, right? So it's not giving it any sort of significant yank that way. All its stretch is due to the rotation. That's kind of what they're saying. It's not due to the fact that we pulled it real quick. Until the center of the rod is positioned on the axis as shown in figure 3. So it's rotating around. We slowly pull it in. The same constant angular speed, omega, is maintained by the motor driving the platform. That is hugely important. You need to clue in on this. This thing gets pulled in, but the motor keeps the thing going at a constant speed. So the motor's doing some stuff here. This isn't freewheeling, okay? So there is going to be a net torque on this system, right? And so you got to be careful. You know, you see the angular momentum, you go, oh, we're going to use conservation of angular momentum. Well, maybe not. Maybe not. Let's see what we got going. All right, derive an expression for the distance that the spring is stretched when the rod reaches the position shown in figure 3. From our initial drawing, we know this is D. This is D. And the spring is like this. And the mass is here. And this is D over 2, which was the equilibrium position. And we want to know what is X. What's that value of X right there? And this is D, right? So therefore, this is D over 2. So this thing is at D over 2 plus D over 2 plus X far out. So we needed to get that straight before we could really do much of anything. So go like that. All right. Derive an expression. We want to know what X is. What's X? What is that thing? What is X? All right. All right. I think we're going to apply some of the forces in the R equals m omega squared R. Right? We're going to apply Newton's laws again. Newton's second law. He keeps showing up all over the place. So what are the forces on here? We got the force of the spring, which is Kx equals m omega squared. And now what's R now? What's R? R is now d plus x. D plus x, right? Because we got d over 2 plus d over 2 plus x. So that's our R. And we want to know what x is. So we end up with Kx equals m omega squared d plus m omega squared x. So I guess we got Kx minus m omega squared x equals m omega squared d. And x equals m omega squared d divided by k minus m omega squared. Right, just factoring out the x, and we got k minus m omega squared. But k is, so x equals m omega squared d divided by 4m omega squared minus m omega squared. Boom, 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 boom. Oh, it's so gratifying. That's so gratifying. D over 4 minus 1, d over 3. Is that right? X equals d over 3. All right, so you have to be careful there with your drawing. You need to, I think that's really the important part here, is making sure you realized that this was d over 2 and get these all laid out. Take your time. Make sure that you got all those positions figured out. Is the angular momentum of the entire system increasing, decreasing, or staying the same? Your first inclination would probably be to think that angular momentum is staying the same. It's not, because there is a net torque on the system. The motor is applying a torque. It was keeping it going at constant speed. How do I know that it is applying a torque? Well, as this mass gets pulled in closer, right? It's like the figure skater. You're spinning around like that, or anybody, remember we took some students, spun around with books, and then they pull their arms in and spin faster, right? That's because there's no net torque on the system. Why do you spin faster? Because your moment of inertia is getting smaller. This moment of inertia is getting smaller because the mass is being drawn in towards the center. It's getting smaller. It would be speeding up if it was freewheeling, but it's not. It's not freewheeling. It's got a motor that's slowing it down, right? It wants to speed up. Well, it's not slowing down. It's keeping it at constant speed, but it's making it go slower than it normally would if it was just spinning like this, right? If it's just spinning like this, and the moment of inertia was getting smaller, this thing would be speeding up, right? In this case, the motor would prevent it from speeding up. The angular momentum is, what's it doing? Is it increasing, decreasing, or staying the same? Is it increasing, decreasing, or staying the same? L equals I omega, right? So initially, I'll call this initial, equals that. Later, L1, when it gets pulled in, I got smaller. Omega stayed the same. So what happened to the angular momentum? I got smaller because it's more towards the center. Omega stayed the same because of the motor. So the angular momentum is smaller. Decreasing is decreasing. They didn't say smaller, they said decreasing. The angular momentum is decreasing because the moment of inertia is decreasing, but omega is staying constant. Got to be careful with that. In order to keep the system rotating with constant angular speed, is the motor doing positive work, negative work, or no work at all? So this thing's spinning this way, and it wants to go faster this way, so the motor has to apply a torque in the opposite direction. It's doing negative work. If it wasn't doing any work at all, it would be speeding up because angular momentum would be conserved. So it's doing negative work. It is taking energy away from the system. On the block in figure 4, draw a single vector representing the direction of the acceleration of the block. Draw the vector so it's starting on and pointing away from the block. All right. It's moving inward and it's spinning around in a circle. So I would draw a sketch. I wouldn't draw directly on that. I would think about what's happening. I would have a sketch on my paper. And so I got this thing right here, this block, and it's going like this, omega, and it's being pulled in. It's being pulled in, right? So, number one, it's going in a circle. So, does it have a radial acceleration? Yes, because it's going in a circle. So, it has a radial acceleration. Now, the question is, does it have a tangential acceleration? Is it speeding up or slowing down as it goes towards the center? As it goes towards the center, this wheel is going at a constant speed. And it's going at a constant speed. If you're starting here, you're going at a certain speed. What happens to your speed as you go towards the center? Right? What's this? What's this? See this little piece of tape that's going around? How does the speed of that piece of tape compare to the speed of something on the outer rim? Right? The outer rim, of course, is going faster than this inner portion. The angular speeds are the same. The number of degrees per second that they're going around is the same. But this has to travel a greater distance. So the things on the outside are moving faster. So this object, as this is spinning around, has a tangential acceleration this way. It's slowing down as it's going towards the center. So it has those two things. So if you add those up, you get that. Don't draw that on your system. They don't want components. So now I had my sketch on a piece of paper, and then I go over to my test booklet, and I got my block here, and I just draw a vector like that. This thing is slowing down as it goes towards the center, because things towards the center of a spinning wheel are going slower than on the outside, and it also has a radial acceleration because it's going in a circle. So there you go. That was 2016 exam. All right. There you go. I will talk to you later. Bye-bye.
Extreme. Fair zone.